All right, let's talk PyTorch. You see it everywhere. It's basically the engine behind so much of modern AI. Today, we're going to tear it down to its studs. We'll start with the absolute simplest pieces, the raw building blocks, and then we'll stack them up one by one until we're looking at the exact same kind of high-performance architecture that powers the huge language models you hear about every day. So let's dive in. So how does it actually happen? I mean, how do we get from something as basic as high school math to a powerful AI model that can generate art or write Python code? It really can feel like magic, can it? Well, today we're going to pull back the curtain and show you exactly how that gap gets bridged. We're building this thing from the ground up.
Okay, here's the game plan. First, we're going to build PyTorch from scratch. Then we'll look at the power of abstraction. After that, we'll cover the training loop essentials. Then we'll scale up to high-performance transformers. And finally, we'll talk about why the future is all about being composable.
All right, first up, PyTorch from scratch. We're building a neural net with nothing but raw tensors. Let's really get back to basics here. Forget all the fancy libraries for a second. We're going to build this thing with our bare hands just to prove that there's no magic going on under the hood. It's all just really, really clever engineering.
And this is the key, the one thing you really need to get. At its absolute core, a neural network is just a bunch of math on tensors. That's it. No matter how crazy and complicated it all seems, it all boils down to operations on these things called tensors. And what's a tensor? Just a fancy name for a multidimensional array. Kind of like a matrix, but with more flexibility. Seriously, that's the whole secret. So, what are the ingredients for our from-scratch recipe? You'd be surprised how simple it is. First, you need some weights. This is just a tensor full of random numbers that the model is going to tweak as it learns. Then you need a bias, which is usually just another tensor filled with zeros to start. The model itself, just a plain old Python function doing a matrix multiplication. And finally, you need a loss function. This is your scorecard. It just measures how wrong the model is. And that's literally it. 4 simple pieces. Okay, we've got our ingredients. Now let's cook. We build our manual training loop. Step 1, the forward pass. We just push our data through the model and get a prediction. Easy enough. Step 2, calculate the loss. We just check how far off our prediction was from the real answer. Step 3, the backward pass. Now this is where the real PyTorch magic comes in. You call this one little function loss.backward, and its autograd engine automatically figures out the gradient for every single weight, basically how much each one was to blame for the error. It's amazing! And finally, step 4, we manually nudge the weights and bias in the right direction to fix that error. You just do that over and over and over again, and that's learning.
Okay, part 2, the power of abstraction, or what I like to call the PyTorch way. Look, building from scratch is cool. It proves it's not magic, right? But it's also kind of messy and a pain to manage. So now let's see how we can do all that same stuff, but using PyTorch's built-in tools to make our code way cleaner, much more organized, and a lot harder to mess up.
First up, let's refactor the model. So before, we had this loose Python function and these separate variables for weights and bias floating around. The PyTorch way, we use NN module. Think of it like a super organized container. It holds everything for us. We can pop in pre-built layers like nn.linear, which already has its own weights and bias built right in. Best of all, NN module automatically keeps track of every single parameter that needs to be trained. So much cleaner. Next, the optimizer. Remember that clunky for loop we had to write to manually update every single parameter? Yeah, that's gone. Say goodbye to that. With torch.optim, we just tell it, hey, here are all my model's parameters. And then when it's time to update, we just call one thing, optimizer.step. Boom, done. One line of code that works whether your model has 10 parameters or 10 billion. And of course, we've got to talk about data handling. Manually slicing your tensors into batches, it's just asking for trouble. It's so easy to make an off-by-1 error, but PyTorch has us covered with dataset and data loader. These things are lifesavers. They automate the whole process, the batching, the shuffling. They can even load your data in parallel to speed things up. It turns all that ugly index math into a beautiful, simple for loop. All right, section 3. Training loop essentials. We've seen all the nice, clean, high-level pieces, but now we need to zoom in on one really crucial detail inside the training loop. This is something that trips up almost everyone when they're starting out, so it's super important to get this right. Okay, here's the big gotcha. When you call loss.backward, you might think PyTorch calculates the new gradients and just replaces the old ones, but it doesn't. By default, it adds them up.
It accumulates them. So the gradients from your current step get added on top of the gradients from the last step. It's like leaving the old numbers on a calculator before starting a new problem.
In 8, don't just take my word for it. The official docs say it right there. Gradients are accumulated in buffers. This isn't a bug, it's actually a feature. It's super useful for some advanced stuff, like when you want to pretend you have a bigger GPU than you do. But for a normal training loop, this is a huge problem. If you don't handle it, your model's updates will be based on a mix of old, stale information from previous batches, and that's not what you want.
So how do we fix this? Thankfully, it's super simple. All we have to do is tell the optimizer to wipe the slate clean before we calculate the new gradients. And there's a function for that. Optimizer.0_grad. You just call that at the start of every loop and you're good to go. A fresh start for every single batch.
And that brings us to this, the complete, modern, 5-line PyTorch training loop. This is it. This is the heart of everything. You zero the gradients, you get a prediction, you calculate the loss, you run the backward pass to get the new gradients, and then you step the optimizer to update the weights. This 5-step dance is the fundamental rhythm for training pretty much any deep learning model you can think of in PyTorch.
Okay, part 4, high-performance transformers. We've absolutely nailed the fundamentals. Now, let's change gears and see how these simple building blocks we've been talking about are used to build the absolute behemoths of AI, the massive, state-of-the-art models like transformers that power things like ChatGPT.
So, what's the secret sauce inside a transformer? It really comes down to this one core operation, scaled dot product attention. You can think of it as the model's ability to focus. It lets the model look at a whole sentence and decide which words are most important to which other words. Every single word gets compared to every other word. This creates this incredibly rich understanding of context, but as you can imagine, that's a ton of computation, especially if you just write it out the simple way.
And I'm not kidding when I say a ton of computation. Just look at these numbers. If you code up that attention mechanism using just the basic math operations, it takes over 87,000 microseconds to run. But if you use a highly optimized, specialized version like flash attention, it's just over 2,000. That is a nearly 40 times speed up. That's not just a small improvement. That's the difference between this is theoretically possible and we can actually train this model in our lifetime. And here's the really cool part. You don't even have to worry about picking the right one. When you use PyTorch's built-in attention function, it plays a little game of what's the fastest tool I have. It automatically checks your hardware, your GPU, and picks the best, fastest backend available. Maybe that's the incredible flash attention, maybe it's another memory-efficient version, or maybe it's a custom C++ implementation. You just call the function, and PyTorch handles all that complexity for you. You get the speed boost for free.
All right, our final section, the future is composable. We're going beyond the basics now. Let's wrap things up by looking at where all of this is going. Because it's not just about giving us these nice pre-built layers anymore. The real power, the future of PyTorch, is about taking these simple blocks and combining them with incredibly powerful function transforms.
This is where things get really mind-bending. So we've got our building blocks like NN module. We've got our super fast optimized functions like attention. The next evolution is being able to compose these things. Just think about it. You write a simple Python function that describes your model's logic, and then you just wrap it in a special function that instantly makes it run way faster by compiling it or automatically parallelizes it for you. That's the idea. And this isn't just a fantasy. This is happening right now. You've got tools like torch.compile, which can give your models a massive speed boost just by getting rid of the slow Python parts. There's vmap, which lets you write code for a single example, and it automatically vectorizes it to run on a whole batch of data at once. No more manual batching loops. And then there are things like jacrev that open the door to the really complex math you need for the next wave of AI research. So think about where we've been. We started with just simple math on tensors, and we built our way all the way up to a toolkit that can build and accelerate world-class, state-of-the-art AI models. The building blocks are simple, the optimizations are incredibly powerful, and the whole system is becoming more and more flexible and composable. The tools are right there. So the real question is, now that you know how it all works, what are you going to build?